Now that we've taken a good look at switch mode power supplies, it's only natural for us to now look at their predecessor, linear power supplies. Now without a doubt, the most obvious difference between these power supplies is the size. Not only is this switch mode power supply way smaller than this linear power supply, it's also significantly more powerful at 50 watts versus 35 watts. But we don't really care how they look on the outside. Let's take a look at what's on the inside. Wow, that's certainly old school. Nice and colourful with all the wires, but we can immediately see that the volume of the power supply is dominated by the size of this very large transformer, which is a full collection of plug-and-play components, which consists of everything we need to build our own linear power supply. These PCBs are from JLC PCB, the sponsor of today's video. JLC offer multi-layer PCBs in 7 different colours, which is ideal for multi-board projects like this one. For example, I have also made use of JLC PCB's excellent colour offerings for my university's Formula Student car, where the colour of board provided a simple indication of the voltage of the circuits. Yellow for voltages between 600 and 150 volts, purple for voltages between 150 and 24, and black for anything under 24 volts. Ordering from JLC PCB is as simple as drag and dropping your Gerber files, selecting any of the many options you want for your board, including the all-important silkscreen colour, and then proceeding to the checkout where you will be even further impressed by their extremely competitive pricing. So when you next find yourself in need of low-cost, high-quality, and maybe even colourful PCBs, make sure to check out JLC PCB using the link in the video description. Right, let's get started. Now the first thing we need is an input to our power supply, and for that allow me to introduce the mains. Now the mains is very dangerous because it's high voltage and has the potential to source very high current. If you touch it, the chances are you're going to die. So please don't do this at home. And as you can see, the first component I've got is a fuse. This is the very first thing our electricity is going to see when it enters our power supply. And it's essentially a very thin piece of wire that heats up when current passes through it because of its resistance. And if too much current passes through, it'll break because it gets so hot. There is a difference between a fuse and just a piece of wire, that being that a fuse is specifically designed to break at a certain current, which is much better defined than just any old piece of wire. Also, something that's very important for high voltage, high current, or DC is that fuses have specific features designed into them to ensure the flow of current is stopped effectively and safely. One of the most prevalent examples of this is fuses containing sand, with the idea being that when the wire inside it melts, the sand will fall into the place of the wire to prevent any arcing, and if there is any arcing and very high temperatures, the sand will be melted and turn into glass, which is an extremely good insulator. This process of stopping the arcing is known as quenching, and the fact that glass fuses like this one don't really contain any of those features is the reason why they should really be avoided, to be honest. But they do look nice, and they make it very easy to tell if the fuse is blown or not, as you can just use your eyes. The next thing to add is a switch, which will let us turn our power supply on and off. There's not a great deal to cover on the switch, except for explaining the reason why it must be on the primary side of the transformer and not on the secondary side, and I'll cover that once we've taken a look at the transformer. Speaking of which, here is the single largest, heaviest and most expensive component of most linear power supplies, the transformer.
Your father knows about saving money. Everything I'm
works is going to take a little bit of time, so bear with me. So a transformer consists of a ferromagnetic core. Typically for mains frequency this will be iron, and for switch mode power supplies at higher frequency it'll be some form of ferrite. To make it a transformer and not just a standard inductor, you're typically going to have 2 or more windings. In this case this is a simple transformer with a primary and a secondary. The primary is connected to the mains input and the secondary is our output. Now to start things off we're going to ignore the secondary and just pretend that this is a regular old inductor. The AC voltage that we apply to the primary winding is going to cause a current to flow, not because of the resistance of the wire, but because of the inductance of the transformer. Now, we have a nice equation for voltage across an inductor, which is V equals L times di dt, which basically tells us that the voltage across the inductor is equal to the inductance times the rate of the change of the current. But we want current, not voltage. So with a small bit of mathematical fiddling, we can see that the current is equal to the integral of the voltage divided by the inductance. In other words, the bigger our voltage, the faster the current is going to increase. So if we start by drawing out a nice sine wave that represents our AC mains input, then we can try and draw the current flow based on this, drawing a line that is steepest where the voltage is highest and is flat where the voltage is 0. As you can see, we actually end up with the same shape as our voltage, It's just shifted by 90 degrees. This is also known as a negative cosine function, and those of you who are mathematically inclined will probably know that negative cosine is the integral of sine. Now, because this current flowing through the primary of our transformer isn't in phase with our voltage, it means that despite measuring just over 30 milliamps of AC current flowing into our power supply, the actual real power being consumed is very little. If we simply multiply the 31 milliamps of current draw by my 247 volts AC supply, we're looking at something in the region of 7.5 watts, which, as we have no output connected, would have to be dissipated inside our transformer. But I can tell you now, this is not warm enough for 7.5 watts. It's only slightly above ambient, to be honest. And this is because almost all of that 7.5 watts we've calculated is actually what's known as reactive power. And what we've just calculated by multiplying the current by the voltage is the apparent power, which is where you just get the RMS voltage and the RMS current and multiply them together. But voltage times current is power. Why isn't it power? Well, if we look back at the waveform we drew earlier and go through the waveform and draw out the power, so that's the voltage waveform multiplied by the current waveform, we can see that the average power is actually 0. So even though we've got current flowing through our transformer, it's not actually consuming any power. And this reactive power is the reason why our power switch must be before the transformer. Because if we put the switch after the transformer, although the real power consumed is going to be very small, the apparent power is quite significant. And apparent power is what dictates the sizing for all components in the national grid. If you look at any transformer, the power it can handle won't be real power in watts, it'll be apparent power in VA. As you can see on this transformer we're using, which is rated for 12 VA or volt amps. And this is just simply because cable and the thickness of windings in transformers are dictated by the current, not the power. So even though this current isn't actually doing anything, it's just going in and out of the loads, we still have to size all of our cables and switchgear and other stuff for this apparent power. Now let's return to our transformer, and it's almost time to have a look at our secondary winding. But just before that, we need to understand how energy is going to transfer between the two windings. And this happens through magnetic coupling. That current that we've just measured that's flowing through our primary winding is going to produce a magnetic field inside the coil, which is concentrated by our ferromagnetic core to stop most of it from just leaking out into the environment. Now, as you can clearly see, our secondary winding is also wrapped around this ferromagnetic core. And an interesting thing happens if you have a conductor like this inside a changing magnetic field. What we get is a voltage induced equal to N times d phi dt, where N is the number of turns we have, and d phi dt is the rate of change of the magnetic flux. Now, the magnetic field that we have inside the core is proportional to the current on the primary. So if we have a look at the waveform that we've drawn for the current on the primary, how do we get the voltage coming? Now, we've already seen that this current is proportional to the integral of the voltage coming in, and the voltage coming out is proportional to the derivative of that current. Now, this is really nice because differentiation is the opposite of integration. So to skip some maths, the output waveform is exactly the same as the input waveform, because we integrate the input and then we differentiate that. So we now kind of know how the transformer works. We put a voltage into the primary, which makes a magnetic field, which induces a voltage into our secondary. But wait a minute, voltage in, voltage out, what's the point? Well, there's two main reasons to use a transformer. First of which is that we've achieved electrical isolation. There is a physical gap between the primary winding and the secondary winding. No electrical connection whatsoever. And for safety reasons, this is an absolute necessity for anything that a human might come into contact with. And the second reason to use a transformer is because of the transformation that it can perform. We can use a transformer to scale the input voltage at the output, and this is simply a function of the number of turns of the primary and secondary windings. That's because the magnetic flux that we put into our core is proportional to the primary voltage divided by the number of turns. And the voltage at the secondary is proportional to that flux multiplied by the number of turns. So essentially what this means is if we have the same number of turns on the primary and secondary, we get the same voltage out as we have coming in. If we have twice as many turns, we get twice the voltage on the output. Or in the case of this transformer, we've got about 20 times fewer turns than we have on the primary, which means our 240-ish volts coming in comes out at a little bit over 12 volts. Now the last thing to cover with our transformer is what happens when we connect a load, so when we draw current from our secondary winding. Well, just like on the primary, any current that flows through the secondary winding is going to produce a magnetic field. However, unlike on the primary winding, this current that we've put on the secondary winding, assuming a resistive load, is going to be in phase with the voltage. And just like how the voltage applied to the primary produced a voltage on the secondary, the current that we draw from the secondary will draw some current from the primary, according to the inverse of the turns ratio. So if we have 20 times less voltage on the secondary than the primary, that means we have 20 times less current on the primary than we have on the secondary. So the overall power on the input and output remains pretty much the same. Now to finish off with the transformer, we're going to take a look at the voltage and current waveforms on the oscilloscope. So first of all, here's the voltage waveform. As you can see, it's fairly sinusoidal. It's not a perfect sine, and that's because I'm looking at the output on the secondary and not the primary. That's because if I connect my oscilloscope directly to the mains, it'll blow up, and I don't have a high voltage differential probe yet. But something quite nice that I do have is a high bandwidth Hall effect probe, which is used for measuring current. It's just like the clamp meter I used earlier, except it has a BNC output that can be connected to an oscilloscope. So let's now have a look at the current waveform.
5,000 years of Chinese music and dance in one night.
Oh, ugh. As you can see, it's not sinusoidal, and it doesn't really look anything like what we expected. Except for the phase relationship, which you can see is indeed the same 90-degree shift as that cosine that we expected. Now the reason for these ugly spikes in the current is that the magnetic core of the transformer has a limit to how much magnetic flux it can hold before it goes into something called saturation, which results in the inductance dropping massively. And if you remember back to when we were calculating the primary current, that was equal to the integral of the voltage, which is the area under this yellow curve, divided by the inductance. So if I zoom in a little bit, this is the zero crossing point. So the integral of the voltage, or the area under this curve, we're going to start counting from here. So we've got more and more and more and more and more flux as we progress along, because the area under the curve is increasing. At this point, our flux reaches the limit that the core can handle, and the core starts to saturate, but the voltage is still positive, so we're still trying to pump in more flux. But the core can't handle any more flux, so the inductance drops, which means we're dividing by a smaller number, which means our current starts to rise dramatically. Now, it's not unusual to have a little bit of saturation in mains frequency transformers, just to squeeze out as much performance as possible from a certain size. I suspect this is a little more than this transformer was designed for, because technically it's rated for 230 volts, and my mains voltage today is 247 volts, which obviously means that the area underneath this voltage curve is going to be a decent amount more than this transformer was designed for. So you might find that at 230 volts, this blue waveform is a little bit nicer. And you can see here I've added a measurement for the RMS current, and it says 33 milliamps, which is about the same as what we got from our clamp meter that we put on earlier. Although we can also see that the maximum or peak current is almost 80 milliamps because of this saturation. And just before we move on to take a look at rectification, I just wanted to quickly show that for some loads, a transformer is all you need. Here we have a 12-volt lamp. It's actually a car headlight bulb, and you can see I can plug it in and it'll happily run on the AC voltage that we have coming out of our transformer. This isn't the case for many loads, but it is worth considering because sometimes it's easiest to just keep things simple, and a basic load like a filament lamp or a heater doesn't care about whether it's being supplied with AC or DC. That's in contrast to a load like a motor, which does care quite a lot about the polarity of the supply. As you can see, when I plug in this motor, it just vibrates. Oh crikey. And that's because the direction that the motor spins is determined by the polarity of the supply. So if the voltage we're putting in is switching direction 100 times a second, which is what the output of the transformer's doing, our motor's going to try and do that too. So clearly there is a need for us to convert our AC coming out of the transformer into DC, and the way to do that is with a diode. A diode is essentially an electrical one-way valve, so it allows current to flow in one direction but blocks it in the other. So by using the diode, we're essentially removing the negative half of our AC wave. So let's take a look at that on the scope. Here we can see the waveform of the output voltage from the transformer that we looked at previously. But if I move the position of my probe to the output of our diode, we can see clearly we're now only getting the positive half of that waveform, with the negative half that should be coming down here deleted from existence. And actually, looking at that number there, the RMS, reveals one of the main problems with using a single diode for rectification, and that's that the average voltage ends up being quite low because we're at 0 volts for half of the time. And that means that when we connect up the motor to the single diode rectifier, it's not going to spin as fast as we'd like it to. And another problem with the single diode rectifier is that we end up with asymmetric loading of the transformer and the mains. And to demonstrate that, I'm going to have to replace this very light load with a bit of a heavier load. So you can see here I have this big high power resistor. I'm going to connect that to the output of our rectifier. And now if we take a look at the current waveform, and I'll get rid of the voltage to make it a bit clearer, you can see how asymmetric this is. If I remove the load, we get that current waveform that we saw before, where, despite it being ugly, the top and bottom sides are the same. But now when I connect the load on the output of our diode, we have a lot more negative current than we do positive current. And to show that that's caused by the diode, I'm now going to flip the diode around. And as you can see, our waveform has also flipped. Not good. And the way that we get around these issues is to swap our single diode for a full bridge rectifier, which is a special configuration of 4 diodes, which essentially grabs the negative half of our input wave and flips it around so that all we get is positivity. It's wonderful. And I can show that on the scope. There we go. Oh, f***. There we go. You can see how we now no longer have the 0 volt sections. We have nothing but pure positivity, and our RMS has indeed increased from about 11 volts to about 14 volts. And as you can hear, when we connect the motor up, it's also spinning faster because it now has a higher average supply voltage. We can now also take another look at the input current, which, as you can see, when I connect the load, no longer becomes all weird and asymmetric. It changes equally in positive and negative cycles, which means we have much better utilization of our transformer. We're not just passing current through it half of the time. Brilliant! The full bridge rectifier is the perfect solution then. Well, I'm afraid there is just one slight downside to this wonderful arrangement of diodes. And that's because when current passes through a diode, there's a voltage drop called the forward voltage, which is fairly constant irrespective of the current that's flowing through the diode. And this is normally about 0.6 volts. So when we have our single diode rectifier, obviously we get nothing coming out of the negative half of our AC wave, but the positive half is reduced by 0.6 volts. Bummer. But now if we consider the full bridge configuration, there's 4 diodes in here, and for either positive or negative half of the wave, we're using 2 of them. So now we've got double 1.2 volt drop, which means that the losses inside the rectifier are going to be quite a bit higher. And that means that a single diode rectifier is more efficient than a full bridge rectifier. And a single diode rectifier is quite commonly used in very low power appliances, especially those without isolation, because then they have no transformer, so there's not so much concern about underutilizing and wasting your transformer. For this reason, some power supplies and some modern DC to DC converter topologies use a special transformer winding configuration called a split secondary, which allows a different type of rectifier to be used. The linear power supply that we looked at briefly earlier actually has such a configuration. As you can see here, the secondary side of our transformer has a black wire and 2 purple wires. So the way to think of this winding is that you've got 0 volts on the black wire and then a positive and negative AC output. And then each one of these is fed through a single diode rectifier. So when this one's positive, this lower diode is conducting and we've got a 0.6 volt drop. Then when it goes negative, the voltage across the other winding is positive. So our current instead flows through this diode and we have a 0.6 volt drop. This means we still have full wave rectification on the output, but we've only got 2 diodes instead of 4, which means less voltage drop. And really, it's quite a smart idea. So we now have an isolated DC output from our power supply. Are we done yet? No. And that's because many loads need a smooth DC output, which our rectifier alone doesn't provide. And to demonstrate this, I have the load of a speaker. This speaker is connected through a DC blocking capacitor. So this represents an audio amplifier, but with no audio playing. So imagine you're listening to a song on Spotify, you've just pressed, and to stop it from doing that, we're going to add a capacitor. So the time has now come to once again have a look at our output waveform on the oscilloscope. And let's quickly remind ourselves of what the output voltage from the rectifier looks like without any capacitor. As we can see, we have that recognisable humped DC, and this waveform is exactly what we could just hear coming out of the speaker. Not great. Let's see what happens now if we add in a capacitor. Ah, that looks much better. As we can see, there's still a little bit of ripple, but overall our DC is much smoother, and you can see the RMS has gone up massively. We're now at 20 volts RMS, because we're pretty much holding the peak voltage continuously. The only reason it drops a bit is because after the peak of the output of the rectifier, the capacitor has to supply all the energy to our load until the next peak comes to charge it back up, which means the load will discharge our capacitor slightly. And we can see that by swapping to a stronger load. So here I have the daddy load, 3 big blue resistors in parallel, and look at that ripple now. The capacitor is really struggling to hold the voltage up, and our ripple is quite significant. Our RMS has dropped from 20 volts down to just 15 volts, and I don't think our speaker would really be getting much benefit from adding this capacitor. So what do we do now? We need a smooth output. We've got our load, we can't do anything about that. Well, the amplitude of this ripple, so how much the capacitor's voltage drops between each half cycle that charges it back up, is inversely proportional to its capacitance. If we put in a bigger capacitor, the voltage will drop less. So let's try swapping our 180 microfarad capacitor for this 5,600 microfarad capacitor. Boom! Look at that. That voltage is as smooth as my Riz, and it's exactly what we need for our amplifier application. So now that we've seemingly solved our problem, let's try reconnecting the speaker and see if the noise has gone away. Sounds good to me. There's a tiny little bit of buzzing still, and that's because speakers are very fussy. You can give them a few millivolts of ripple and you might be able to hear it, and that's why audio amps have massive capacitors relative to the amount of power that's going through them. Now, nothing's perfect, and there is one major downside to adding a big smoothing capacitor, and that comes in the form of power factor, or more specifically quality factor. And this is essentially how sinusoidal our current draw is. Now, because of the saturation in our transformer, even with no load, the current draw of our power supply is pretty poor. I think you'd be hard pressed to say that this is a sinusoidal waveform. But watch what happens when I add a big resistive load to the output of our power supply. We end up with a new, even bigger spike. And this is caused by the big rush of current that's needed to charge the capacitor back up for every half cycle, to fill in all that energy that the capacitors had to supply to the load while the voltage has been lower. And these current peaks manifest themselves on the input current to the power supply, which gives us this very ugly waveform. This problem can be completely fixed with something called active power factor correction, which is something I'm going to cover in an upcoming video. But power factor correction gets into the realm of modern power electronics, and the complexity would be a completely pointless addition to a linear power supply. You might as well just go switch mode at that point. And most high power switch mode power supplies do in fact have active power factor correction. Thumbs up for regulations. Now, just like a young electrarch in the back of the car on the way to the Lake District, I can hear you all shouting, "Are we there yet?" Not quite, I'm afraid. We have one more problem to solve with our power supply. And that's that many loads require a specific voltage, and that voltage needs to be stable irrespective of changes in mains voltage or load. And at the moment, our output voltage is affected by both of those. As you can see, with no load connected, we have a beautiful, perfect 22 volts. But if I connect a small load to our output, that 22 volts drops down to 21 volts. And if I bring back daddy load from earlier, 14.6 volts. That is shocking, and shall not be tolerated. What we need to keep our output voltage constant is some form of regulator. There's a few ways that a regulator can work, and I've made two different ones to show the two most common types, that being open loop and closed loop. And these are very similar, but we're going to start by looking at the open loop, because it's not as good, and that's the order that things are always done. Now the job of a linear regulator like this is very simple. It has a target voltage to achieve on the output, so let's say 12 volts, and it needs to introduce a voltage drop that brings the input down to 12 volts, no matter what the input is, or how much current is being drawn. So for example, as we could see before, when we have no load, our capacitor is charged to 22 volts, so our regulator would need to drop 10 volts to get 12 out. Whereas when we put daddy load on, our capacitor voltage drops down to just 15 volts, meaning our regulator only has to drop 3 volts. But how do we implement such a circuit? Well, at the heart of almost all regulators is something called a Zener diode. So let's take a look at that. So here I have a Zener diode. As you can see, it looks just like a normal diode, and sometimes it's quite hard to tell the difference. Until, that is, you apply a voltage to them. And that's because Zener diodes conduct electricity in both directions. What's the point of that? It's just a wire. Well, in one direction, they're just a standard diode with our 0.6 volt drop, which we'll be able to see if we apply some current through it. 0.6, 0.7, close enough. But where Zener diodes make their mark is when you flip them around. Now if we turn on the power supply, we can see we're getting a voltage drop of about 6 volts. That's a lot more than the 0.6 we had before, and the voltage drop that you get across a Zener diode, when it's reverse biased, can actually be hand-picked. If you go online and shop for Zener diodes, you can buy 3.3 volt ones, 3.6 volt ones, 12 volt ones. You can get whatever you like. But what's really special about this reverse voltage drop is that it changes very little with current. As you can see, we currently have a very small amount of current flowing through, less than 10 milliamps. But if I increase this current, the voltage drop barely changes, 6.1, 6.2. Now, let's take a look at this open loop regulator circuit, because it's incredibly simple. Here's our input, here's our output. The negative connection passes straight through. This is our Zener diode, and this is a series resistor. The positive connection of our input voltage is here, and the shared negative is here. These two pins are joined together, just like this schematic shows. What this means is that a current is always going to flow in this direction, from the positive input down to the negative. And as we've just seen, a current passing through a Zener diode is going to result in a fixed voltage drop. So even if our input voltage changes, which would mean the current changes, the voltage across the Zener is going to stay almost exactly the same. So can we just connect our output to here? No, because then our output would be connected through this resistor, which would result in a voltage drop when a heavy load is connected. So what we have to do is we have to buffer this nice voltage to get a voltage at the output that's the same but stronger, so the load can't pull the voltage down. And that is what this final component is for. This is a bipolar junction transistor, or BJT, and by connecting the reference to the base of the transistor, we form what's called a voltage follower, which does exactly what we need. The only slight downside is that this transistor is a bit like a diode. It introduces a 0.6 volt drop, so that means our reference voltage needs to be set 0.6 volts higher than what we want at the output. So let's connect this to the circuit and see what happens. As you can see, with no load, we're looking at about 13 volts. And if I connect to the weakest of my loads, it drops a little bit. And firstly, that's because this 0.6 volt drop in the transistor is a bit like a diode drop. It increases as more current passes through. So we're going to be getting more voltage drop at higher currents inside our transistor. And then also, the more current that we draw, the more current the transistor is going to draw through its base, which is current coming out of our voltage reference, which means that eventually our reference voltage is also going to get pulled.
Hate ads? Here's how to block them.
Now that we've taken a good look at switch mode power supplies, it's only natural for us to now look at their predecessor, linear power supplies. Now without a doubt, the most obvious difference between these power supplies is the size. Not only is this switch mode power supply way smaller than this linear power supply.
Sponsored by Brilliant. This is not electricity. You can't see electricity. You can only see its effects, such as light, heat, motion, magnetic fields, very expensive bills, and electric arcs. Take this simple circuit with a battery, a switch, a lamp, and a wire connecting them all together. The battery is adding energy to the circuit, and the lamp is removing this, transforming it into light and heat. We can flip the switch to control this. What's happening is tiny particles called electrons are moving through the wire from the battery's negative terminal through the lamp and into the positive terminal. They actually move a very small distance, but I'll explain that in just a moment. Many of us were taught that electricity flows from the positive to the negative. That's because long ago, Benjamin Franklin theorized that electricity was an invisible fluid. He rubbed a glass rod with a cloth, which then gave him a shock. He believed the cloth was adding more of this fluid, making it positive, while the person touching it had less, which made them negative. So he assumed that electricity flowed from positive to negative. Schools then taught this information, many still do, and we call this conventional current. Some years later, Joseph Thomson experimented with a cathode ray tube, a device with two metal plates in a vacuum. When powered, a strange ray appeared, and it oddly travelled from the negative to the positive side. He observed that a magnetic field influenced the ray's direction. He also noticed that when passed between electrically charged plates, it deflected in the electric field between them towards the positive side. As we know, like charges repel and opposites attract, so the beam must be made of tiny particles with a negative charge that moves from negative to the positive. He called these particles an electron, and we call this electron flow. Unfortunately, Benjamin Franklin had guessed incorrectly. The cloth was removing electrons from the glass rod, and they were moving from the person to the rod. The common analogy is that the battery is like a pump, providing the pressure to push the current through the circuit. We measure this electrical pressure in the unit of volts. For example, this battery is rated to provide 1.5 volts, and this one is rated for 9 volts. The water flowing through the pipe is similar to the electrons flowing.
This is a transformer. In a simple way, it can be described as a device that step up or step down voltage. In a step up transformer, the output voltage is increased, and in a step down transformer, the output voltage is decreased. A step up transformer will decrease the output current. A step down transformer will increase it. This keeps the system input and output power equal. The transformer is a voltage-controlled device. It is widely used in AC power distribution and transmission.
The CIA has particular skills in developing relationships. Life is all about relationships.
Today we're talking about electrical basics. Now this presentation is, or this class, is a very, very long class. This thing has like 200 slides in it, so obviously we're not going to do 200 slides. But we are going to cover some electrical basics. All right, so we're going to talk about electrical basics. This is one of my favorite illustrations to kind of get a sense of the difference between the different names of what's going on with electricity. Now, the first thing is sort of a caveat, because this will eventually be on YouTube, and anytime anything's on YouTube, we get electrical engineers who love to show how smart they are, and they like to point out that most of the metaphors that we use are literally just for us to get our heads around things. It's not like how it actually works, but it is a way for us to understand how it works. So we think about voltage or potential. So I give the other names for these things here, which is the same thing. So voltage, also called potential. We think of that as being the force or the pressure behind the electricity. So if you imagine a water tower, the force is actually because you have a difference in height between the water tower and where it's eventually going to go. So that potential would be represented by the distance between the water and the water tower and the reservoir where the water is going to end up, right? So higher the water tower, the more potential or more pressure.
Welcome back to another how-to video from Electronic Control Services. My name is George Merchant. I'm the owner of ECS, and you can check us out on www.improvedmaintenance.com. No D in there, just Improved Maintenance. And today we're going to be talking about how to use a multimeter. So a lot of common misconceptions with multimeters, even people that have been using them for quite a while, don't kind of understand exactly how it is that they work. So I'm just going to break it down and make it as simple as possible. We're going to start with this right here. I think everybody probably recognizes a tape measure. A good old cheap. Just borrowed this from one of my cohorts.
Hi, I'm Josh Bloom. Welcome to another video in the RSP Supply Education Series. If you find that these videos are helpful to you, it certainly helps us out if you could give us a big thumbs up and subscribe to our channel. In today's video, we want to talk about a very useful skill when dealing with any kind of electrical system. Whether it is your own home and you're trying to figure out why your outlets aren't working, or complex situations like why you aren't receiving the signals that you might expect. The skill that I am referring to is electrical troubleshooting. And today we want to provide you with a few simple tips and tricks that can help you.
This is what the perfect gift for a man looks like. Bold, badass, and built to impress. When my wife got me...
When I bought this house, on the home inspection report, it was noted that none of the breakers inside of the electrical breaker box were labeled. Today, I'm going to label the breaker box. To help me do that, I'm here alone. I've got this Klein circuit breaker tracer. This is the ET310. I've got my receiver, and I've got my transmitter that plugs into receptacles. I've also got some wires that I'm not sure where they go to that are for smoke alarms, and I'm going to use this attachment along with the receiver to find those wires. Let's jump right in.
When plugging this transmitter into the receptacle, I want to make sure the last two lights are illuminated, which indicates that it is correct wiring for this transmitter to work properly. This will stay in the receptacle while I go to the breaker panel and use the receiver to find out which breaker is feeding the transmitter.
I'm going to turn the receiver on by pressing this gray button. And what I'm going to do is, first I'm going to do a sweep going down and then up. That's going to be our learning sweep. Second one, I'm going to do the same thing. That's going to be our locate. On the second time, we should be able to locate the breaker. If not, hit the reset button and try again. So here's our learn sweep, holding the receiver horizontal. And right now, we are just learning the panel. Now we are going on the locate journey.
You're here because you're interested in Claudio's problem in this house behind us. Claudio's kitchen lights haven't been working ever since he moved in, and 2 electricians have taken a look, but they couldn't find the problem. So we're going to check it out. Claudio?
Jordan? Claudio, hi.
Nice to meet you.
You too? Please come inside.
Thank you. So I understand you have a tricky electrical fault.
Yeah, so we've got under-counter lights in the kitchen, which haven't worked since I moved into the property. We've had someone try to fix them initially. Through a builder, we had some work done in the house when we bought the house. The builder said he's an electrician, he can sort this all out.
Oh, builders who are electricians, that's already...
and yeah, he said, no, he'll be back into, he's definitely going to do it. And we kept pestering, when are you going to come, when are you coming? He said, oh, I'll be there, I'll come. And he just didn't bother to pitch, and eventually we just lost communication with him. We then contacted another local electrician who claimed, well, he can sort this out for us, no problem. Came and spent a couple of hours trying to isolate the fault. He said, no, it looks like there's maybe a short somewhere, he needs to come back for probably a day to try to find the fault.
Okay.
He booked us in for a day. I said, cool, go for it. Didn't hear from him again for about 2 weeks. I contacted him and said, please don't forget about us. He said, don't worry, I've booked you in. This is your date, end of the month. I'll be there on Friday, 25th. Friday the 25th came, dead air, nothing. Silence. No phone call, no text message, nothing. I was like, what? Yeah, so I was a bit desperate. And obviously I've been following you guys on YouTube. All the work you do is so meticulous and it's like top tier. I thought I'll just contact you, Jordan, to say, well, can you recommend somebody in my area because I'm so desperate. And yeah, thank you. You said that you prepared to help today, so.
We're here to give it a go. So we like a good fault, so.
Yeah, I mean, like I say, if you can fix it, it'd be awesome.
Yeah.
Because I really want it working, but let's see how we get on.
Okay, do you want to show me the lights and we'll see what the situation is?
So it's in the kitchen, we've got these under-counter lights on both sides.
Okay.
And we know they were working before.
Yeah.
This is the switch on this side of the wall here.
Yeah.
And the cable's disconnected on the switch. So I've had it myself one day, put it in, switched it on, and it just blew the mains.
Was it disconnected when you moved in?
Yes.
Okay.
Yeah. Somebody said to me, well, just check if the switch is faulty. So I took the switch off.
Yeah.
And the cable was disconnected.
Okay.
So I wired it in.
And now you know why it was disconnected. Bang. Okay, and when the previous electrician came and did his investigation, what did he do?
So basically, he said there's transformers at the top of the cupboards.
Yeah.
He said it could be one of them gone faulty, so he's tried to isolate them. He's basically, I think, cut them off at the wall, each of them.
Right, okay.
Then when they were all off, power on, it's still tripped. And he said, don't worry, I'll cable them back up. I haven't actually looked to see what he's done.
Okay.
Because he said he'll get back to fix whatever he's done anyhow.
Yeah, yeah.
So yeah, I don't know what the state is up there. He reckons there must have been a screw or a nail through the twin and earth somewhere.
Through a cable.
And he didn't know where the junction box was or how to get
multiple circuits.
Not multiple, it's like the main earth leakage goes, so the plugs go, everything.
The RCD trips,
the RCD,
basically.
yeah.
Okay, fine. Okay, so this is your consumer unit, classic BG consumer unit, as our viewers will know, one of my favourites. Was this already in here when you moved in? This
was
unit?
yeah.
Okay. Do you know which RCD was tripping?
If memory serves correct, I think it was the lights and this one on the left.
This one here.
Yeah.
Okay.
Maybe when we moved in, that builder I spoke about.
Yeah.
Installed these plug sockets in the garage for us.
Okay.
I don't know why them in there, so it might be that one. I don't know.
I love it when builders do electrics. It's fantastic. So I'm going to do neat or not neat on this consumer unit first of all, and just have a look to see if there's anything obvious in here. You can definitely tell that builders wired the sockets up in here. Oh my goodness. Been kind of like lashed in there. He's wired 3 cables all into one circuit breaker. But apart from that, it's all the original house wiring, so it's the red and black wires. So I'm guessing it's going to be one of these that has the problem. We'll go and have a look behind that light switch and see if there's anything obvious there, and then run some tests.
Awesome.
Right, so we're going to start by just taking this switch off. There's a couple of things I'm looking for here. Is it just a permanent live and switch line, or is there a neutral here? If there's a neutral here, it's going to make it a bit easier for us, because presumably the switch live and neutral going out to the lights will be here, and therefore we can actually do a test on the individual cable that goes out to the lights, but usually quite unlikely for a property of this age for that to be the case. Yeah, so unfortunately we're not in luck. It's a new twin and earth cable, and that'll be the permanent live, and then that'll be the switch line presumably, although it's not identified. If you look at the back of this box, so the whole box is loose, which is not a good start. And there's no grommet in the back, so the cables are not protected. So we'll screw that box back and we'll try and put a grommet in just to tidy that up. But first, let me do a test on these wires and see what the readings look like. So while I'm starting to check out the testing on this switch, I've got my beautiful assistant here, Tom, who's going to have a look up above the units and see what's going on up there.
Oh, hello. Well, that could be the reason why it's going bang. So you've got a connection point up here, which is broken off, twin and earth coming down, and it looks like the neutrals going out are in with the earth on the connection point.
It's probably that classic DIY or / builder thing where they put all the blues together and all the browns together.
But they've put the great there,
and this is actually wired as a live and neutral, whereas it should be a live and switch line.
Yeah.
In which case, it's like the most classic DIY blunder ever, but it's so easy to fix if you know what you're doing. Let's hope it's that.
Yeah, there you are.
Hey guys, I thought I'd make another video here. I had a few comments on that last video on the power station, on how to do some of the wiring. So in this video, I want to go over how to do the Y connector, where I combine 2 LFP batteries to make a 25.6 volt input to my power station. So let's get going with that. Okay, for the parts needed, I'm going to put a link down in the video description for Amazon. That way, if you don't have these parts already, you can make sure you get the correct ones. And the first thing we're going to need here is the XT60i female connector. This is what identifies for the EcoFlow power station, whether we're going to draw 8 amps or 15 amps from the connector. And if you connect the center pin here to the negative side, which is the beveled side, that will tell the EcoFlow, hey, I want to draw 15 amps from this connection. If you connect the center pin to the positive side, which is this square side of the connector, it'll tell the EcoFlow, hey, we only want to draw 8 amps from the connection point. So anyways, for the battery sides, we're just going to use these XT60H connectors, the male side of it. That's these guys here. And what I'm going to do is show you how to do a Y connection, which is just going to be 2 of these connectors. But we could do up to 4 of these LFP batteries in series and get about 51.2 volts. You won't exceed the input voltage rating of the power station, but we'll just do 2, and that'll give us 24 volt input, which is 25.6 volts technically. But anyways, let's get going with that. Okay, for the actual wiring, I'm going to use this 14 gauge wire. I pre-stripped most of the ends of it for this video, but I'll strip one to the correct length here. I'm using 14 gauge because it's super flexible. It's stranded wire. This is 105 degree C wire. It doesn't need to be that exotic, but you can use in these XT60 connectors up to 10 gauge wire, but this stuff is really rigid and hard to work with. And the chassis rating for free air wire for 14 gauge is around 32 to 35 amps, I believe. So it's more than sufficient for this use. And let's go ahead and get this end stripped off of here. Okay, to strip the ends of those wires, you pick the correct wire gauge size in your stripper. And I'm stripping these to about 1/4 inch because these connectors, some of them have a recessed connection on them like this, but these guys don't have a recessed connection, so this is about where we're going to strip this to so it fits in there. I'm going to end up actually having to cut a little piece of this wire off so it fits correctly, but I just want to show you. I had to cut off maybe about 1/10 of an inch or so. So let's get that done real quick here. Alright, so that fits in there nicely. So the reason I want to cut it to that length is because when you put the cover on, you want it to actually cover the wire portion of it so it doesn't short to anything. So let's get going to the next step here. Okay, so before we solder these, I just want to show you real quick. Most of these connectors are marked with the positive and negative of the connection. There it is. On the connector just below where the housing covers it. So that way you can be sure you're making the correct connections. But anyways, just want to show you that real quick before we solder it. I'm going to use these needle nose here just to hold my connector kind of so it doesn't dance around while I'm trying to solder it. And let's see, we'll set that positive connection on that wire there, the red wire. You don't have to use red wires or blue wires or black wires. It's just, I like to use standard wiring colors just to identify what connections.
Hi guys, my name's Bill, and what I want to do is show you how to test a wall outlet and how to troubleshoot it when it's not working. Alright guys, so here's the scenario. Your refrigerator quit working, maybe it was your washer, your microwave, coffee pot, maybe it's a plug-in electric heater or something like that, but whatever it is, it's not working, and you don't know why. It could be that whatever's plugged into the outlet is bad, or the outlet doesn't have any power. So the first thing you want to do is locate the panel box in your house, which is going to look similar to this, and I'm sure you guys know where it's at in your house, and you want to look for any tripped breakers.
And it's going to be pretty obvious. One of them is not going to look like the others, and it's going to be in the off position. So of course what you want to do is reset the breaker. So maybe you reset the breaker, now your refrigerator's working again, or your microwave, or whatever the case may be. So what could possibly have happened here is that breaker has gotten weak over time. And it just happens. If there's a lot of current that goes through that breaker on a daily basis, or over a period of time, that breaker will get weak and trip at a lower amperage. So in a case like that, you just want to replace the breaker. I'm not going to get into that in this video, but I will in a future video. So make sure you subscribe to my channel, and I'll get to that. But let's say no breakers are tripped. So all the breakers are on, there's nothing tripped, but you still don't have power at your outlet. So let me show you a couple different ways you can check that. One being without tools, and then we're going to get into, with a meter and a plug tester and stuff like that. Okay, so the first test without tools that you can do to see if the outlet has power or not, or if the appliance is broken, is
I just started using the free ad block from Capital One Shopping, and you need to too. It's a desktop extension that blocks all ads on my favorite.
I must say that you are completely wrong. If you are one of those who think that diodes are very simple, I must say that you are completely wrong. It is really unfair to think that diodes are very simple components and they can only rectify current. In this video, I will talk about diodes and their application, not inner structure or chemistry, and introduce 3 main types of diodes with 8 application of them in circuits. Please stay with me in the rest of this video. Diodes, these little components, are so tricky. They put out of sight their talent. Maybe they are afraid of being used in your project. But don't worry, I will reveal their secret in few minutes. To begin with, I'm gonna take a brief look at ideal diode. This is a schematic symbol of a diode. It has 2 pins, anode or positive and cathode or negative. There is a line in cathode side of real diodes to specify a negative or cathode side. Look here, this silver line here, and this one. And this diode specifies cathode side by a black line. If you change this line to a shape like S, first letter of Schottky,
This is a Zener diode, one of the most common diodes in electronics. Whoever invented this diode is a real genius. In this video, I'm going to walk you through everything you need to know about Zener, so stay tuned until the end. It is specifically designed to function in the reverse direction. A Zener diode is a highly doped semiconductor device. It is engineered with a wide range of Zener voltages, VZ, and certain types are even adjustable to achieve variable voltage regulation. But how does a Zener diode work in reverse bias? A Zener diode works similarly to a regular diode when forward biased. However, in reverse bias mode, a small leakage current flows through the diode. As the reverse voltage increases and reaches the predetermined breakdown voltage, V's, current begins to flow through the diode. This current reaches a maximum level determined by the series resistor after which it stabilizes and remains constant across a wide range of applied voltages. There are 2 voltages and a current characteristic of a Zener diode, which are 1. Forward characteristics of Zener diode. The first quadrant in the graph represents the forward characteristics of a Zener diode. According to the graph, the forward characteristics of the PN junction diode are nearly identical. 2. Reverse characteristics of Zener diode. When a reverse voltage is applied to a Zener voltage, a small reverse saturation current, IO, flows across the diode. This current is due to thermally generated minority carriers. As the reverse voltage increases, at a certain value of the reverse voltage, the reverse current increases drastically and sharply. So now let's talk about Zener diodes applications. 1. Zener diode. As a voltage regulator, the Zener diode is used as a shunt voltage regulator for regulating voltage across small loads. The Zener diode is connected parallel to the load to make it reverse biased, and once the Zener diode exceeds knee voltage, the voltage across the load will become constant. The breakdown voltage of Zener diodes will be constant for a wide range of currents. 2. Zener diode in overvoltage protection. When the input voltage is higher than the Zener breakage voltage, the voltage across the resistor drops, resulting in a short circuit. This can be avoided by using the Zener diode. 3. Zener diode in clipping circuits. The Zener diode is used for modifying AC waveform clipping circuits by limiting the parts of either one or both half cycles of an AC waveform. So now I hope I have given value to this video about what a diode is, and I hope you enjoyed this video. If you do so, please like, comment, share, and subscribe for more educational videos about electronics. Have a wonderful day. Peace and love.
If the toilet gets clogged in the future, don't use your hands to clear it. Just learn this trick.
Frequent clogs are often accompanied by foul odors. No matter how hard